Well, good afternoon, everyone. Uh, Today we have the honor of having here Professor Gabriele Giuli from the University of Camerino, Italia, and he's going to talk, he's going to explain and discuss a bit with us some of the differences and comparisons between X-ray absorption spectroscopy and X-ray diffraction, both synchrotron-based or not only?
Diffraction of the laboratory.
Okay. So thank you very much, Gabriele, and the floor is all yours.
Okay. First of all, thank you for hosting me and also for coming to this seminar. I prepared a short seminar on the comparison between X-ray absorption spectroscopy and X-ray diffraction. They are two now widely known techniques, each one with some advantages or some disadvantage. And what I would like to show is how they together can give complementary information on the material we are going to study. To make a presentation short, I think within about 1 hour, I restrain myself from putting an equation and any details of the technique. So we will just say practically the information we can get from those two kinds of techniques, both alone or combined together. So briefly, we will see what we can say first by X-ray absorption spectroscopy on the oxidation state of some chosen element, on the local geometry, meaning if I put an element inside the host crystal or inside the glass, what can I know about how it is bonded to the surrounding atoms? And also some hint about how dopants locally modify the host structure, which is actually my field. Most of my career, I studied how a dopant can enter into a structure, glassy or crystalline, and how it changes locally the structure around him, or the reverse, how the structure changes the environment around the dopant. And we will say something also about amorphous sample. So, to be extremely short, X-ray absorption spectroscopy requires a highly collimated X-ray beam of high intensity and the possibility to tune the energy. So it's a technique that is mostly done in a synchrotron radiation environment. So a synchrotron is schematized here. There is some device which allows to create a very strong and fast X-ray beam. This X-ray beam possesses a lot of different energies. So usually it is used a couple of crystal or even more crystal to select which energy you want to use and to be able to scan our sample with a range of different energy. There is a possibility to focus the mirror down to less than 1 micrometer. So it's possible to do also microprobe. And then according to which kind of detector you use, and in general on the setting of the experiment, you may study the X-ray emitted by the sample in response to the incoming radiation, or how much this sample absorbs X-rays. So basically you measure the incoming intensity and the transmitted intensity, or for the fluorescence intensity, and the logarithm of the incoming over transmitted or the fluorescence over the incoming gives a curve like this, which is basically how much the sample absorbs the X-rays as a function of the energy. So this is how an X-ray absorption spectrum looks like. For any element, there is a specific energy at which there is a jump in absorbance. So there is basically a step here. Iron has this jump at approximately 7,112 electron volt, cobalt 7,700. Each element has its own electronic transition which occur at a definite energy. So if we decide to study the range of energy across an iron absorption edge, in that way we study the chemical and structural environment of iron. In this sense, this technique is an element selective technique. So if we have a material where both iron and cobalt, for example, are present, choosing the appropriate energy range, we can study alternatively either the iron, either the cobalt, which already is a big difference with X-ray diffraction, because in X-ray diffraction, what you see is how the electron density changes. So if you have both iron and cobalt in a structure, by diffraction alone, you cannot discriminate by them. In this case, instead, choosing the appropriate energy range, we can decide which element we are interested in, we can study. And if we look more in detail on this basically step in the absorbance diagram, we can discriminate three different regions. This is the edge region where the step occurs. Well before, few electron volts before the edge, there can be some peak, which is called the pre-edge peak. And usually for transition elements, it is a 1s to 3d electron transition, which can give information on the oxidation state of the transition element of interest. Here there are some very broad oscillations which result as a sum of many different frequencies. Each frequency represents the distance between our photoabsorbing atom and the atoms which are nearby. So each one, this signal can be decomposed in several different frequencies. Each frequency basically represents a distance of neighboring atoms. So from this region, we get a radial distribution function. How many atoms there are at which distance from the absorber we are studying. And basically, the same principle of this region applies also in this region, but with a difference. Basically, here we have this jump is due to the fact that you are expelling inner electrons in a state called continuum, where this electron is delocalized within the whole structure. So this electron behaves like a wave, which can be scattered by the neighboring atoms. In this region, the scattering goes from the photoabsorbing atom to one atom and back, which is called single scattering. In this region, it is like photoabsorbing atom, one atom, another, and back. And with many possible different combinations. So in this region, we get information only on the radial distribution function. How many atoms there are at a certain distance and of which kind. Here, there is an information which somehow depends also on the bond angle. So here, it is in principle possible to get information also on bond angles and in general, not only to the radial distribution function, but also to the local geometry. And, So, let's try to disentangle which kind of information can we get from each one of those regions. This is a normalized absorption spectra, which means that we normalize the difference in it between the background here and the average of this region here to 1, so that we can compare the spectra in a similar way. And here there are spectra of different sulfur compounds, from a sulfide to a sulfite to a sulfate. And we can see grossly that in some cases there is a very large energy shift of this absorption edge according to the oxidation state. In this case, it is exaggerated by the fact that sulfur can go from 2- to 6+. So there is a 8 oxidation number difference. Here we can see different sulfides, while for sulfate the spectra looks more or less all similar one to the other. What changes is only the frequency here. So for sulfides, instead, there can be large difference also in the exact position of the absorption edge. And the absorption edge, by convention, is taken as the inflection point here in the writing edge, which is taken from the first maximum of the first derivative of the absorption spectrum. And if we, by the first derivative, compute the edge energies of a set of sulfides, a sulfide and several sulfates, we see that sulfates are all grouped in a very narrow range of energies, whereas the sulfides are spread over a certain range of energy. Why? Because the position of the edge energy does not depend only on the oxidation state, but also on a number of other factors. Let's see some. Here, again, to say the same concept, a number of manganese compounds. Those are the first derivative spectra of the XAS spectra shown here. And here are computed the edge energies in electron volt of those compounds as a function of the nominal oxidation state of manganese. Again, here we go from 0 for the metallic manganese to +7. So also in this case, there is a very large range of shift in energy of the edge energy. But again, if we look not only those in the literature, but we take a large group of divalent manganese model compounds, we can see that there is a very large range of energy. So the edge energy can give us a gross idea of the oxidation state, but most times not a very precise number. And one of the motives is that here are the absorption spectra of aluminum. And we can see that there is a certain shift of up to 2 electron volts. So it may look small, but it's still sensible. Between albite, where aluminum is only in tetrahedral coordination, andesite, when it is in 2 kinds of coordination polyhedral with 5-fold and 6-fold coordination, and in grossular, where aluminum is only in 6-fold coordination. So the edge shift, the edge energy depends not only on the oxidation state, but also on bond distances and in general on bond type. That's why it can give us a very crude estimates, but not very precise numbers. And if we go at the iron cage for a large series of iron model compounds, both normally divalent and trivalent, here there is a range of edge energies. The solid symbol is the average, grand average, for the divalent and trivalent model compounds. We can see that the edge energy, iron can vary, if we don't account for metallic iron, to 2+, from 2+ to 3+. And most trivalent are here, most divalent are here, but there is also some divalent up to this position and some trivalent down to this position. So we can see that there is a large overlap between those 2 ranges. That's why you have to be very cautious when giving an oxidation state only on the basis of the edge energy. If we look instead at the centroid energy of this peak here, which is small, especially in the early times, people didn't like to work on small peaks. But if you work on the pre-edge peak of iron, and the same model compounds shown here and here, you see that they plot in a very narrow range of energies. There is still a range that's not a unique value, but it's quite narrow. And trivalent model compounds all plot here. All the ones shown here. So the pre-edge peak can be a small feature, sometimes it's 6 times smaller than this, very often actually, but it can be a more reliable estimate of the iron oxidation state. And if we plot the energy of this pre-edge peak, and 0 refers to the edge energy of metallic iron, which is 7,112 electron volt, all the divalent iron model compounds have pre-edge peak in this range of energies. And all the trivalent iron model compounds have pH peak in this very narrow range of energies. And if we look not only at the energy, but also at the intensity of the pH peak, model compounds with a coordination number, so how many oxygen iron is bonded to, of 6 or higher, plot in this region of intensities. 5-fold coordination, like in Grandi derive, for example, plots at this intensity. Tetraederally coordinated divalent iron plot in this range of intensity of the pH peak and energy of the pH peak. Trivalent iron model compounds, according if it's in octahedral, this is a square pyramidal, and this is tetrahedral coordination, can plot in this range of intensity shown here in the graph. So the pH peak can give us an indication not only on the oxidation state, but also on the coordination environment. And how accurate can it be to determine an oxidation state? Usually in the geologic literature, most people prefer Mossbauer. Let's see if also X-ray absorption spectroscopy can be useful and with a similar precision. This is a set of pH peak taken for a set of silicate glasses synthesized at controlled oxygen fugacity with a different mixture of carbon monoxide and carbon dioxide. And this is how varies the pH peak from the most reduced to the most oxidized. We can deconvolute the pH peak with 2 or 3 different components. Usually 2 is more than enough. And by computing the centroid energies, which is the average of the energy of the component times the relative area compared to the total area, and their integrated intensity, we can get a trend like this. So a point in itself is not a precise number, but we can model a weighted combination between 2 end member that we choose. In this case, if we choose this end member and this end member, each dot represents a 5 mole percent fraction of trivalent iron with respect to divalent. And they all plot along a very narrow trend. And we can, from comparison with the computed weighted average of those 2 end members, determine a ratio between 3 plus and 2 plus. In this case, the trivalent iron is only 4-4 coordinated, only in tetrahedral coordination. The divalent iron, as it happens in most silicate glasses, is in a mixture between tetrahedrali coordinated iron and 5-4 coordinated iron, with some minor amount possibly of also octahedrally coordinated divalent iron. We get a certain amount of number of the iron redox ratio 3 plus over the total iron. And if we compare the one computed by X-ray spectroscopy and the one determined by titration, we see that they plot on a 1-to-1 line with a very small error. So if we are good with a relative error of 5%, then this technique is good. If we require an error of an iron redox ratio plus or minus 1%, maybe this not be the most useful technique, but very often it can be one of the few techniques able to compute a number. Why? Because titration you can do when you have enough sample with a large enough content of iron. Similarly, also Mossbauer, you need some amount of sample and some concentration of iron, and also long collection times, according to the state of your radioactive source. How much sample do we need for this kind of experiment? In theory, 1 milligram is enough. And how much iron content do we need? According to the set of the experiment, according to your patience and your skill, you can go down to few parts per million of iron.
Could you move the mouse? It was the cable.
So, you may be happy or not with this error. I didn't specify. According to the quality of the data, this error bar can be 3 sigma or 1 sigma. Sometimes plus or minus 5% is a 3 sigma error. However, you may be happy or not with this kind of error, which is anyway something good. But in some cases, it is the only method to get a good number. For example, if we are working with impact glasses, if you have a macrotectite, which is a glass spherule maybe 200 micron wide, with a low iron concentration, that's, I think, the best possible way to determine the iron oxidation state. Iron has a small pH peak. If we go to titanium on the left-hand side of the transition element row, we get pre-peak as low as this up to almost as high as the edge jump. Why? Because being a 1s to 3D electronic transition, the emptier the 3D shell, the most pronounced the transition. Here I plotted the integrated area of many pH peak according to the number of electrons. So that's copper 1 plus, which is a full D shell, has a zero transition probability. The more you go to empty the shell, the more the transition of the probability increase. And again, tetraederally coordinated compounds are usually the highest transition intensities, and they lower a lot with increasing coordination number. And this is another element just to see a different kind of elements. This is vanadium with different model compounds, with different oxidation states and coordination numbers. And in this case, the pH peak plot a different intensity and energy according to the oxidation state and coordination number. So vanadium 5 plus can have a pH peak at this energy and this intensity. Or if you increase the coordination from 4 to 5, you go down to this intensity and increase the energy. Vanadium 4 plus plots here and here according to the 5-fold or 6-fold coordination. Vanadium 3 plus, which is mostly 6-fold coordinated in octahedral coordination, usually plot in this range. So let's see some comparison and see when for some kind of information it's better to ask diffraction or it's better to ask X-ray spectroscopy. This is the structure of an orthopyroxene. We can see a stretch of the linear chain of tetrahedra. This is M1 site, this is the M2 site. I synthesized a whole set of orthopyroxene from pure ferrocylite to 90% astatite. We made structure refinement by powder diffraction data, which was the only choice because it's very difficult to synthesize single crystal big enough for single crystal data. So if you have the occasion, if you have the chance to have a single crystal diffraction is always best. But if you don't manage because you are working with synthetic samples, then you downgrade to powder X-ray diffraction, which can give anyway very precise information on the unit cell parameter, sometimes even more precise than a single crystal, because you can use an internal standard like silicon, for example, but can get information also on the atom coordinates. So, for example, that's the average size of the M1 octahedron, the average size, the MO distance of the M2 octahedron, the solid symbol are the powder data, the empty symbol are single crystal data from the literature, so they compare nicely well. And this is the XAS spectra we collected for all the series of orthopyroxene. We see they are grossly similar. We will not focus in this case on the pH peak because we already know that the iron is totally divalent. There is some small small difference in the peak here. This single peak tend to increase due to at least two components, but their contributes tend to split more and more when we go to the high magnesium end member. And also the top of this absorption maximum is split into two maxima, and in the iron-rich end member, the first, the A peak is higher. On the magnesium end member, the second peak is higher. It's possible not only to simulate the region at high energy, the so-called XAS region. It's possible to simulate also the region close to the edge. It is much more complicated. It may take few months to have a good fit, but at the end we managed to simulate both the contribution of the iron in the M1 and 2 peak and do a sum for different compositional ranges. And basically we saw that according to how much iron we put in one or the other site, we can even model the amount of iron in the M2 versus the M1 site, which is called the occupancy of the iron in the two octahedral sites. I think I didn't touch something.
You're touching this cable, yeah. It's very sensitive.
Okay, I'll try to.
Let's see if it stays. Where is it?
I like you. Tem um jeitinho lá de coisa?
Ou esse aqui?
So what's the outcome of this trial? That we managed to get some information on how iron is distributed to two different sites, which are even similar to different octahedral sites, which is not trivial with XAS. Honestly, what should I say? If you have a single crystal, go for single crystal. The occupancy of an element between two different sites is best by single crystal. If you then don't have single crystal, you can try powder. The occupancy you get is slightly less accurate. XAS would be the most difficult part to get this information. But again, in case you have an orthopyroxene with very little iron content, both single crystal and powder won't give you anything because they are sensitive to the average electron density. So if you want to have a hint on the occupancy, even if in this case with a gross error, you can still rely on this technique because it does not depend on the concentration. As far as you manage to simulate good XAS spectra, the information you have is fairly accurate at whichever concentration of iron. Another case, this is basically the structure of a phlogopite, a tetraferric phlogopite, in which in the tetrahedral layer we have both silicon and iron. The iron is mostly in the tetrahedra. There is a very little bit in the octahedra. In this case, what do we get from diffraction and what do we get from absorption? This is the spectrum in the high energy side, so we don't see the edge which is here before that range, and here we exaggerated the amplitude of those oscillations. By a careful fit, we can determine the iron-oxygen distance of the first shell, iron-silicon distance, iron-oxygen distance of the third shell, and so on and so forth. And the most reliable parameter is the first shell iron-oxygen distance, which is about 1.85 angstrom. What does diffraction tell us? Diffraction tells us only about the average size of the tetrahedron, because unless the the entry of iron determine a symmetry different tetrahedron, if it enters in the same tetrahedron as silicon, then diffraction can tell us only the size of the average tetrahedron. And that's the size of the tetrahedron that diffraction tells us. What do we expect for the silicon-oxygen distance? If we do an average on few thousand structures where silicon is tetrahedral coordinated, we have an average of 1.62 angstrom for all the silicates. So that's a distance we expect being it a silicate with silicon in tetrahedral coordination. So again, what do we get here? We get that diffraction gives us an average distance weighted by the occupancies of silicon and iron in the tetrahedron. More or less, we have 3/4 of the tetrahedron occupied by silicon and 1/4 of the tetrahedron occupied by iron. So the picture we get from diffraction is very precise for all the coordinates, but when talking about the tetrahedron, where we have two different atoms with two very different sizes, it gives us only an average picture, and this is what those are the sizes we expect for the silicon occupied by tetrahedra occupied by silicon, and this is the size we expect, we measure, we determine for the tetrahedra occupied by iron. How is it possible that in the same structure we have so different tetrahedra? In the case of phyllosilicated, it's easy. That's a tetrahedral layer seen from above, and actually you can adjust the tilting of the tetrahedra and the rotation. And so, if you rotate this tetrahedron, for example, in a way or in another, you can adjust a much larger tetrahedron within a set of smaller tetrahedra. So in the case of silicate, it's mostly easy to accommodate large cations like iron in a tetrahedral layer, because by adjusting the rotation and tilting of all the other tetrahedra, you can accommodate the possibility to host some much larger tetrahedron. And that's a statistical plot for different sets of tetraferric phlogopipes with different amount of iron in the tetrahedron, and actually we expect exactly, we see the same results we see from here if we assume that the iron-oxygen distance is the one we determine in one sample. So, in some cases, the structure can locally adapt a lot, even when you insert an atom, which now we call a dopant, in a place where it shouldn't enter because it's too small for him. What happens in the case of another kind of structure, like corundum? In the corundum case, we have a hexagonal close packing of oxygen, and part of the octahedral sites are filled by alumina, plus some minor amount of chromium, for example, for Rudy, or iron, for example, in the yellow sapphire. If we look at the end-member compounds, in alumina, we have this aluminum-oxygen distance. In escolite, we have this chromium-oxygen distance. In hematite, which is a structural with corundum, we have this iron-oxygen distance. And this is a old paper by the French group by Garay and co-worker, where they measure the chromium-oxygen distance for corundum with different chromium contents, and they say that actually there is, at low chromium content, the chromium-oxygen distance is much lower than that of the end member. Let's see what we have with iron in a kind of gem called the yellow sapphire. I skipped the part of the XAS. We determined that the iron is completely trivalent, with no significant amount of divalent iron in the one we examined. Octahedral coordination, of course, we expected that. And that's the XAS spectrum. So it is actually a very good fit, because we go to a very high energy and we managed to simulate all the oscillation up to this energy. And the distance we find is 1.95 basically angstrom. I didn't mention the error in the XAS refined interatomic distances is of the order of 100 of an angstrom, whereas in single crystal usually is 1,000 of an angstrom. So hematite at this distance, trivalent iron in the corundum has this much shorter distance. Why? In the case of a tetraferrofluoropyrite, you have a certain degree of freedom for all the tetrahedra to rotate and tilt, and in that way to accommodate neighboring tetrahedra with much different size. In the case of the corundum structure, we have an hexagonal close packing of oxygens. So if you try to enlarge one of the octahedron, you have to strongly modify the size of at least 6, if not 12, neighboring octahedra. In this case, the structure does not relax around the dopant. So basically, the structure says to the dopant, if you want to enter, you have to take the space we let you have. And no possibility to strongly modify, locally distort the structure of the constant. This is another case of a silicate, a garnet. Now they changed the name because they found a different member. But anyway, it is a garnet where in the tetrahedral side they have both iron, aluminum, and silicon. And in this case, iron is a majority, occupy the majority of the tetrahedral site. I synthesized a garnet, that's the iron oxygen distance found in a phosphate, roloitoite, in the tetraferrofluoropyrite I showed you before. In quartz, in phonolytic glass, in rhyolitic glass. So in most silicate, apart from quartz, which is another story, the iron oxygen distance is close to this value, about 1.85 angstrom. That's a, we don't see a picture, okay, not important. That's a diffractoram, that's a ritual refinement of this synthetic garnet, in which 3/4 of the tetrahedral side were occupied by iron and 1/4 by silicon. We have a fairly good disagreement index of the structure refinement. So that's a resulting unit cell parameter with a very low error. And those are the coordinates of the oxygen atoms. All the other atoms are in special position, so we don't need to specify the coordinates. And that's the average structure as seen by diffraction. So we have a certain defined average tetrahedral oxygen distance, a zirconium oxygen distance, and that's in the octahedron here. And the average calcium oxygen distance in the distorted default site here. Let's see the spectrum. That's the XAS spectrum. That's a very large pH peak because in this case we have purely tetrahedral coordination for the trivalent iron. That's the fit of the pH peak. And that's where it plots. So we can be sure that most of the iron is trivalent and in tetrahedral coordination. And that's the fit of the high energy portion of the spectrum. So we sum up all the frequency we calculate according to the structure. We fit them to match the experimental spectrum, and that's the result. The residual, the red line is the theoretical, and the blue dots, empty dots, are the experimental. And we find, not unexpectedly, this distance here. In this case, that's the iron oxygen distance we determined by XAS. That's the iron tetrahedral oxygen distance as determined by X-ray diffraction. And this is a range of silicon oxygen distance determined for a set of n-membered garnets studied in the literature. Again, the distance we found from diffraction is a weighted average between the iron oxygen distance and the silicon oxygen distance, weighted by the relative abundances in the tetrahedral site. So we have to modify this structure, and we have to allow for the fact that some tetrahedra are larger than the other. and difficult to imagine. We may try to redo the refinement, splitting the position of the oxygen into two different positions. The disagreement index is the same as before, so it's compatible with this model, the diffractoram, but it's not definite proof that we can model all the structure with a split oxygen position. So basically, we assume that some of the oxygen are in a position and some of the oxygen are in a slightly different position. And basically, those will be the structure with all the tetrahedra of one side, so or all the tetrahedra of the other side. It's not only a matter of the relative size, also the distortion of the tetrahedron is different. Here it's more compressed along this direction, here it's more elongated along this direction. So still to work on this kind of material, because oxygen splitting is one possibility, but there may be another. And the open question is, how do these different tetrahedra are distributed in the structure and how they interact with the rest of the structure? So we are going to do some other, not only TEM work, but also on another single crystal technique if we manage to get enough good data, where you see also the background between the peaks. Just into amorphous sample, and for the sake of diversity, I put 3 peptides. Those are 3 peptide molecules which do not form crystalline material. They are X-ray amorphous. So from X-ray diffraction, we cannot get much. We know their general aspect, but we cannot refine the coordinate of all the atoms. And one of the problems is that, according to the chemist who synthesized this molecule, in at least one of them, there was a significant amount of trivalent copper, which is an exotic oxidation state for copper. Let's see. This is the same spectrum of copper for cuprite, copper monoxide with divalent copper, and a ditellurate cuprate in which copper is nominally trivalent. The pre-peak is not this. The pre-peak is very little small potato here. And if we subtract a background and isolate the pre-peak, that's the pre-peak for divalent copper oxide, and that's the pre-peak for trivalent copper oxide. So both shifted to higher energy and to higher intensity. This does not have a pre-peak because it has a complete D-shell, and so it's not possible to have a 1s to 3D transition. Those are the 3 peptides we showed before, and actually one is purely divalent, one has a very small proportion of trivalent, and one is completely trivalent. To make a very long story short, also the XAS data, they are not beautiful, but that's what we managed to collect on those peptides. Peptides has another problem with respect to minerals. They tend to decompose under the beam. So we have first to study how long they resist because they can be decomposed, and collect 30 or 50 spectra, short ones, average them to get the decent spectrum. So the XAS data, so the refined copper-nitrogen distance, are compatible with trivalent and divalent copper. And in this case, we managed to calculate also the theoretical XAS spectra. And also from the theoretical XAS, we managed to confirm the copper-nitrogen distance and confirm the fact that the copper is not exactly in plane between those 4 nitrogen, but is slightly out of plane, which is something that we suspected from the pre-peak, but we couldn't be sure of. And, okay, still in time, just a small hint on silicate glasses. What is a glass? A glass is an amorphous sample. Amorphous doesn't mean that the position of the atom is completely random. Cations are anyway surrounded by anions, and several cations have a specific preference. So silicon in low pressure glasses is mostly tetrahedral coordinated. So does aluminum, at least for geological composition. For when you go to some exotic composition, aluminum can display also some other kind of coordination. And iron, when it's divalent, is both tetrahedrally coordinated or in a trigonal bipyramidal coordination, mostly. When it's trivalent, it's mostly tetrahedrally coordinated. It's important to get information on the iron. Apparently, yes, because what we realized in the case of few synthetic phonolite, those are the viscosity of those phonolite at different temperatures, and we realized that the same melt, but with different redox ratio of the iron, changed slightly the viscosity, increasing for higher iron oxidation state. Why? Those are the coordination we inferred for the different possible coordination environment of iron in those classes. Those are the ones we measured. That's the XAS spectrum we measured. And what we found is, in another sample not shown here, where iron is completely divalent, the average iron oxygen distance is close to 2 angstroms. In the sample where iron is mostly oxidized, the iron oxygen distance is close to the one we found for terraferric logophyte for the garnet, close to 1.85 angstrom. So what happens when we oxidize a silicate melt? Two things happen. Here, iron has at least two different coordinations, so a coordination number close to 4.5. Here is purely 4. So when you oxidize, you increase the fraction of tetrahedrally coordinated cation, which means you increase the polymerization of the melt. Furthermore, when oxidizing, you reduce the iron oxygen distance in the tetrahedron from close to 2.0 angstrom or 2.05 angstrom down to 1.86. Shorter bonds means stronger bonds. And even if not quantitatively, that helps to qualitatively explain why oxidizing a silicate melt, the viscosity increases. How much it increases is a matter of temperature. So increases higher at the lower temperature. Few hints on the time remaining to us, to some mineral material, synthetic analog of a mineral, which is used in the field of lithium-ion batteries. So, what happens in a lithium-ion battery? Imagine to have here trifilite, LiFePO4. It's a mineral with the same structure as olivine, where lithium is only in the M1 site and iron only in the M2 octahedral site. What happens where we charge the battery? Lithium migrates towards the cathode and intercalates into the anodes of graphite, into the layer of graphite, in that way causing a flux in response to a flux of electricity. And when the lithium-ion battery is in operation, the reverse happens. So lithium goes back from the graphite to the cathode. And what happens to the structure of the cathode? The olivine structure stays the same. Just the lithium side gets vacant, and the iron in the octahedron oxidizes from 2+ to 3+. So it is a reversible transition, and lithium can go out and in response to charge and discharge of the lithium-ion battery. A very short introduction to lithium-ion batteries. We have several material kinds. It doesn't matter now if we put them in the cathode or in the anode. The lithium can go in and out the structure, leaving the structure basically unaltered. So we call it insertion if lithium can move in 1 or 3 directions, and intercalation in case of layered material. Or lithium can go in alloy with the material. For example, if we have crystalline silicon or a metal, lithium can go in alloy with that material, creating an alloy between the original metal plus lithium. In this case, the volume difference is very large. Or lithium can enter in a structure even zircon, for example, even zircon, which is a refractory material, can serve as a cathode, as an anode. Lithium can enter the zircon structure, completely amorphizing the structure, or even decomposing to some component oxide, amorphous, mostly. And in this case, it is called conversion. So those are the three names for the three different mechanisms for lithium to enter a structure. And let's see one material which is familiar to us, which is this triphyllite, which is a lithium iron phosphate with the olivine structure. Don't tell too much. Okay. I have to skip something because otherwise we don't. Just say that for different kind of material, why do we study doping? Because even though the material is the same, according to different dopants, the electrochemical properties of this material change, sometimes a little, sometimes considerably, sometimes really by a large amount. Let's focus on our mineral. So this is the M1 site, which makes chains branched by M2 sites at their side. This is the phosphate tetrahedron. And basically, the lithium goes in this way, diffuse from one octahedron to the other, and can exit the grains of lithium iron phosphate, creating region of FePO4, which is heterosite, mineralogically, olivine structure, trivalent iron in the M2 and M1 vacant. And basically there is the heterosite grows at the expense of the triphyllite during charge. The reverse happens during discharge. This is the material we synthesized. They are mostly nanocrystalline. This is the structure refinement with how much the unit cell parameter change if we dope the structure with some vanadium. And here we have two questions. Does the vanadium really enter the structure, or does it create an island of an impurity? Because many people just put something in the oven, say, okay, I synthesize this with this doping, I make a patent of this. But how can we sure vanadium entered the structure and in which site it entered? So first do structure refinement of a series with different vanadium doping contents. There is a trend in the unit cell variation, so actually we are pretty sure vanadium entered the structure. Not only we are sure, but we managed to simulate perfectly the spectra, the same spectra, so we know that vanadium is in the M2 site like iron. These are the spectra of the material pristine and charged materials. And we see that all the press peak of vanadium are close to the trivalent member. And they do not go much closer to, they should go here because it's octahedrally coordinated vanadium 4+. So there is some scatter because the condition of synthesis were enough to obtain iron perfectly divalent, but there was some oscillation and there was some minor amount of vanadium 4+. But basically, what we get is that in the doped material, vanadium does not participate to oxidation. Iron instead oxidize a lot. The blue one are the pristine material, the red one are the charged material. We can see there is both a considerable shift in the edge and also in the pre-edge peak. We can calculate exactly the amount of the redox ratio between trivalent and divalent iron. And if we do for each compound with a different doping, the exact difference of trivalent to total iron of the pristine and charged material, we realize that the more vanadium we put, the more we manage to oxidize almost 100% of the iron present. It's not trivial to oxidize all the material present. Every material has a theoretical capacity, so how much lithium you can lose and regain, and usually they never go up to 100%. but little doping of vanadium managed to basically change, that's the efficiency basically, managed to change the efficiency of the material from somewhere 70% to almost 100%. Why? Our explanation is that in order to introduce a trivalent cation replacing a divalent iron, we have to introduce beforehand a vacancy in the lithium M1 site, and the M1 chain with some vacancy maybe helps the diffusion of lithium along the chain. Okay. Another case of a mineralized material used for lithium-ion batteries, this time on the anode. This is zinc oxide doped with iron. From diffraction, we see two things. We can see clearly how the unit cell changes according to the amount of doping of iron replacing zinc. But also we see that the peaks get much larger. And from that, we can derive a crystalline size for the synthetic material. In this case, we see that a very little amount of iron contributes to decrease a lot the size of the crystallites, rendering it nanocrystalline. Okay. Those are the spectra. We determine the iron oxidation state of the synthetic material, the same for some material doped with cobalt. I will try to make it short. This is the XAS data from which we got the distance, the size of the tetrahedra containing the dopant. This is a Wurtzite-like structure. And we noticed that from the electrochemical curve, something was happening in the first stage of oxidation. This, in theory, this material would be just a complete amorphization of the material when lithium enters, but we seem to look at some intercalation before the amorphization occurred. So we try to stop the process in this stage and get the XAS spectra in this stage. And we found out that that was a pristine material. At this stage here, the amount of the iron, divalent and trivalent, was almost half and half. What we think happened? Two things. First, if we introduce a trivalent for a divalent, we must create a vacancy. And as one vacancy must compensate for two iron, we postulate there is some clustering. So the iron are not randomly distributed along the structure, but they form cluster. And they form clusters also with a vacancy. What we think happened, but actually then we made other experimental data on the electrochemistry, and this confirmed our hypothesis, is that before entering the structure, making it amorphous, the lithium was able to enter the vacant tetrahedra, reducing one iron every two. So in this case, a local probe can allow not only just to get crude numbers like iron redox ratio, but also to get some hint on how iron is distributed on the structure and get some suggestion about the clustering of both iron tetrahedra and vacancies, and the possible use of that vacancies for an intercalation before amorphization. The same stuff was confirmed also in situ, so we put the battery inside this pouch aluminum bag under the beam, and we follow the process, in this case at the zinc edge, but we did the same at the iron edge, to see how the structure got progressively amorphous, and by accurately analyzing also the XAS, we found that not only there was a formation of one alloy, but two different alloys, a pure zinc alloy and a lithium zinc alloy. The last one, effect of iron doping on the cerium oxide. It is not the future material for batteries. Why? Cerium is expensive. It was just a trial to see how it worked. And what we expect, lithium, 2 should enter in those empty cubes, because that's the only space left. And when each lithium enters, one of the cerium atoms must oxidize, must reduce from 4 plus to 3 plus. In this case, the structure is in the anode. That's why we have the reverse. Lithium enters and it oxidizes. We made all sorts of diffraction in the lab, diffraction in situ during the battery working, XAS and XAS, ex situ and in situ. So to make a very long story short, iron is completely trivalent. And that made me discomfortable because trivalent iron, we already saw some distance when we talked about some other material. Trivalent iron is a small size cations. How can it fit in a plasma, in this very large cube? So we did an accurate XAS, and we saw that actually the iron oxygen distance is such that it cannot be at the center of the cube, but it goes to the face of the cube, which is a very strange behavior, never observed before in the literature, both in natural or synthetic material. And the other surprise was that checking at the number, it looks to me that the amount of lithium it accepts is almost double of the theoretical one. And we already said that usually the real capacity is a fraction of the theoretical capacity, not exceeding 100%. In this case, we get almost 200%. And getting more trials, we get up to 250% of the theoretical capacity. What's happening? We made also theoretical calculation of the structure to see, does the calculation also are compatible with iron staying at the face of the cube instead of the center? Yes, they are compatible with. What if lithium also, instead of going to the center of the cube, go to the face of the cube? That in the structure, sorry for going back and forth, in the structure, you can have more lithium per each cube. And that can explain why this structure theoretically should accept 1 lithium each cerium for each cerium atom. Actually, it accepts 2.5 lithium each cerium atoms. And that's the material we got the cover of this journal here. I like the artist paid from whom depicted lithium ions like meteorites. That's why I like this cover. Okay, concluding remark. I wouldn't spend much time on what we saw in the battery research. But what I would say is that dopant in any material, not only lithium-ion batteries, can affect the physical properties little, very little, or very much considerably. So how a dopant, the localization of the dopant, already the fact that if it really entered the structure or created micro to nano inclusion is important to know. But how the dopant affects the local structure can have considerable interest to try to understand why the physical property change according to which kind of doping and to the amount on doping. And in that sense, mineralogy is a technique that is very useful also in other fields, not only in mineralogy, but in chemistry, in material science, in coordination with other people from the physics department or from the chemistry department or even engineering department. More in particular, more in detail, this is already told, but one of the take-home messages from this talk is that I made a very long story extremely short, but apparently simple phases like zinc oxide, magnesium oxide. For our geologists, magnesium oxide is a major phase in the lower mantle. It is an apparently very simple phase. But according to the dopant, in the mantle mostly iron, according to the fact that it is trivalent or divalent, if there is a considerable amount of trivalent iron, we can expect magnesium oxide to be mostly nanocrystalline, for the same reason that we saw it for zinc oxide. So apparently simple phases can reveal a very complex behavior according to the kind of doping and to the amount of doping. So in that sense, combining different kind of techniques, long-range order techniques like diffraction, and short-range order technique like X-ray absorption spectroscopy can reveal unexpected complexity that we didn't dream about. And thanks for your attention. And this was an exception of this. Right.
Thank you very much, Professor. And we have time for a few questions. Do we have any? Gabriel?
I know that manganese has a lot of minerals from oxides and hydroxides minerals, and usually when you have a thin section, it's pretty hard to differentiate the many minerals there. Do you think that we can make this differentiation in the oxidation state and the coordination from these manganese minerals using, for example, the science technique?
I think that science can be part of a picture together with different techniques. I have experience mostly on iron oxides, and many iron oxides have spectra which are somehow similar. So relying only on XAS and XAS to differentiate between different manganese oxides, which has a very varied crystal chemistry, I wouldn't do that. But coupling this with different techniques, this can get into the iron manganese oxidation state. There is some complication. Of course, I showed the nice part, but okay, let's do even this one. It's fine. Here we see 3H peak. Hematite, for example, has another transition right here, which is very well known. We studied to see if it was a dipole or quadrupole transition, and also manganese has trivalent manganese. So divalent manganese model compounds are easy to be studied with XAS. Trivalent iron model compounds have a further transition here, which has the same energy as the prepeak of 4-valent manganese. Again, what does it depend on? It usually, this extra transition appears when you have two neighboring trivalent manganese oxide. And basically, it is an electron cell transition between the two neighboring manganese via the shared oxygen. So, for example, when you have a chain of octahedra with two neighboring trivalent manganese oxide, you have this extra transition, and you see, oh, look, we have also some 4+ manganese, and actually it's not. So the interpretation is not only straightforward. It's good to have some experience on a large variety of model compounds. And when you're studying a subject, it's good to have many different model compounds with different oxidation states and coordination numbers. So you get a hint on the complexity of the system. But yes, for sure, the XAS can help in that.
Yeah, we were working with some manganese oxyhydroxide, and we do see the Young-Teller effect in the Raman spectroscopy. Mm-hmm. So we can have more or less an idea of the 3 or 4+, but we still have a problem to narrow more and more exactly mineral that could be found.
I think that it could add something to the picture. Not alone as a technique, together with other techniques, but yes.
Okay, thank you.
Manganese is one of my nightmares, by the way. I have lots of data of manganese which I never published. François Farge published something on the manganese, and yeah, it's a complicated picture.
Yeah, yes. I prefer iron.
Me too.
Well, can I ask a question?
Well, of course.
You have shown many spectra on the K edge. Do you also work on the L edge? Because sometimes it gives more information on the neighborhood? What can you tell us
Okay,
about
in
it?
the literature, it often says that iron edge spectroscopy, XAS spectra give more information than K-edge. Why? Because people don't like to work on small features like the TH peak, and in the early days, there was a slightly more pronounced variation of the position. The edge spectra of iron are somehow similar. There. Are somehow similar to this spectrum. And there was a considerable shift of few electron volt from 2 plus to 3 plus. So in LH spectra, they don't have a pre-H peak, but from the splitting of this maximum, they could infer a qualitative determination, but it was something you would see by the naked eye. So you didn't have to fit, and so they said. My impression is that it is not more quantitative than the KH, for the case of iron at least. Again, you choose which edge. I did try the edge of iron and also of other elements. According to which is the compound you are studying, you are choosing which is the edge you can collect with the best accuracy in terms of energy calibration. And also, for example, in theory, you can collect any edge, but if you have two elements and you have the K alpha emission line of one element overlap with another line of another element, you cannot use that, and so you cannot use the K edge. You have to use another edge. In this case, you are forced to. The same consideration used for the K edge you can do for the L edge, but for the fact that you don't have a pH pattern for transition metals. And so you can still work with XAS. Is more difficult because we are at much lower energy. But you can do XAS. You can work also with theoretical XAS spectra. So it's just more difficult, but it's not impossible. And you don't have the pH peak. So my personal opinion is that if you cannot access the K edge, you use the L edge, but in my opinion, it's not more precise than the K edge. And of course, for example, for iron, being at much lower energy, the X-ray is much less penetrant. And so you're looking not really only at the surface, but your observation is biased toward the surface instead of the bulk of the sample.
Okay.
So it's a matter of choice. You choose which edge according to the demand of your experiment.
And of course, you have to work under vacuum. There are more complications to work.
Vacuum is not a problem nowadays.
Yeah. Well, any other questions or comments? Not. Let's thank Gabriele again.
Thank you.